Kia ora koutou, welcome to Passive House New Zealand. Te tōpuntanga o te whare koro te Aotearoa. Thanks for joining us in this session of Passive House Season webinar series. We have 1 to 4 series, and our talk for series 1 and 2, which is past, is now recorded and it's available on our website. Today's series is number 3, and it's about EnerPHit. EnerPHit has been developed for refurbishment of existing buildings. It is not always possible to achieve full passive house standard. We have a fantastic lineup for you today. The speakers today is Priscilla Besson from AUT, Daryl Sang from Sang Architects, and Jason Quinn from Sustainable Engineering. We will have a Q&A at the end or during the talk if time allows, and please post your questions on the Q&A or chat and have them available set for everyone so we can share our knowledge. First of all, I'd like to welcome Murray Durbin from Envelop Solutions, who is our main sponsor for the seminar today. Over to you, Murray.
Good afternoon. Good afternoon, everyone, for logging in. I'm just going to share my screen now with our presentation. I'm from, as introduced, from Envelop Solutions. We're a New Zealand-based and owned business focusing on high-performance homes and certified passive houses. We represent a window manufacturer in Germany called EnerPHit, and along with EnerPHit, we are diamond sponsors for FINS, for the Passive House Institute, and are proud of that. The products and services which Envelop offers, just to give you a little bit of a rundown, if you haven't heard of us before or haven't come across us, or we have been growing recently both in staff and product ranges, so there may be some new things you haven't seen. Starting at the top left-hand corner, we work very closely with ProClimber for their external wraps and internal membranes, and we install their products in quite a few parts of the country. We do MVHR, balanced heat recovery ventilation. We're doing 4 different products now: Blauberg, Stiebel Eltron, Zender, and Eartesi. And we have installers to do insulation. We do home automation, the windows and doors, as I mentioned, EV car chargers, hot water solutions, either by heat pumps or pellet boilers. And we have a couple of Minneapolis blower door machines in Auckland and Christchurch. We can offer blower door testing out of each of those regions. We can travel as required as well. So the Envelop team is growing. So there's myself and a new shareholder, Tim Riley, who joined us earlier this year. Leanne, my wife, and she looks after operations and Homestar related work. Cam is our South Island area manager. Sue's our specialist designer for MVHR. Kat's logistics. Mark's our driver and storeman. Magdalena Szynczka is joining us next week as our BDM, primarily focusing on windows and doors. Mike Knowles will be starting with us shortly as a lead installer for MVHR on the North Island, and also window technician. He's an LBP certified builder. And Dale is our lead installer in the South Island. Has been installing windows actually for 4 or 5 years now before joining us, so it's great to have him on board. Very quickly, EnerPHit, it has been around for 150 years. Philip EnerPHit still runs it, and they've done around 80,000 projects right around the globe. They've recently been primarily bought out by a company called the IFN Group, and they're about a 700 million euro company based out of Austria. And that's given us a few options recently where we were unable to get products out of Germany in a good time. So we've got factories in Austria and other parts of Europe that we can now access. In IFN, they've earmarked about $300 million for new technologies and new products in the next few years. So it's a fantastic organization to represent. This is just a very small selection of what we have access now out of Europe. PVC ranges, 4,000 right up to 8,000, and Energettos and EDs, wood, alu, and a range of aluminium profiles as well. And here's a new profile that we've got a few jobs or new to us. It's a slimline profile. May struggle with passive house down in the lower parts of the country, but in certain homes it may be suitable. Front doors, if you're struggling for a nice front door look on a EnerPHit retrofit or your new build, we've got several hundred options available in sort of the good, better, best range, and you can view all of those either in a steel composite carbon fiber door or just a natural wood door if you have a nice and close space for your front door. Lastly, I know there's been a lot of talk around roof windows, and it is something that we are able to supply for EnerPHit jobs as well. We want to bring a bit more light into the home as a passive house certified quadruple glazed roof skylight, center pivot skylight that we can now bring down, or we are bringing down out of Europe. There's a vast range of products available and sizes. We're focusing on a 780 by 980 and a 780 by 1.4 meter or 1400 size, and in a format which is suitable for bathrooms and laundries and essentially humid areas as well. And it comes standard with an installation kit and a air tightness flashing kit as well. So that is my brief introduction to Enveloped and the team and what we do, and wish you good luck today with your fantastic presenters.
Thank you, Murray. Wonderful to have you in for today, and great to have you on board. We're now delighted to welcome Priscilla Besson from AUT, and she's tuning in all the way from Brazil. So welcome. And her talk is on Heritage for the Future, integrating EnerPHit to seismic upgrades of historic buildings in Aotearoa.
Thank you very much, Mei Ling. So I'll just share my screen. Can you hear me okay?
Yes, we can hear you.
All right, great. Okay. So thanks for the introduction, Mei Ling. Thanks, Murray, as well. Very happy to be presenting today at this really nice webinar, such an important topic for us in Aotearoa. So my name is Priscilla Besson. I'm currently a lecturer at Huri Te Ao School of Future Environments at Auckland University of Technology. I'm originally an architect from Brazil, and I'm a certified passive house designer. Been living in New Zealand for the past 7 years. But yeah, at the time, right now, I'm visiting my parents in Brazil and a bit jet lagged. So sorry if I'm a bit slow with my presentation. But bear with me, it will be all right. So my talk today will be focusing on retrofitting historic buildings in Aotearoa. So I will be presenting some key findings from my research at the University of Auckland. So my PhD focused on retrofitting unreinforced masonry buildings in conjunction having energy and seismic retrofit opportunities for these buildings. So as I'm the first one speaking, I thought I would start with a little bit of a talk about the big picture of why retrofit is so important. And to me, I heard this quote a few years ago, and it really influenced my work in my PhD research, talking that the greenest building is one that is already built. We have so many buildings already here, so many beautiful buildings, historic buildings. We have many other examples that are not historic, but are existing structures with all these materials and all this embodied carbon in place that we should really be reusing and trying to keep and adapt for the future. So there's so much work needed in terms of retrofitting in New Zealand. We know all the issues that we have in terms of indoor environmental quality, thermal comfort, and energy efficiency in many of these existing buildings. But there's so much that we can do in terms of energy retrofits, and EnerPHit is such an important standard for this practice. So talking about my research more specifically, I wanted to work with historic buildings more specifically. I wanted to work with retrofit, and then I started to think about all this historic heritage that we have in New Zealand and everywhere in the world, and what's going to happen to these buildings as we look into climate change, as we look into how to adapt them to suit our current needs, to make them more energy efficient and comfortable for occupants. And I'm very passionate about historic buildings and about history. So that was one of the inspirations for this work. Also, personally, I was living in a historic building at the time that I started my PhD. So that was also a big impact on my studies, as I was really experiencing what it was to live in a 1930s heritage building in Auckland. A very, very cold and inefficient building, lots of condensation, mold, and all those things that we all know about, I'm sure, as we are in the Passive House webinar. Most of you are already very familiar with all these key issues in the New Zealand building stock. So one of the things was also to think about what was happening in New Zealand at the time, and thinking that one of the key issues for heritage in New Zealand is to think about earthquakes and seismic strengthening. And if we think about more of a holistic view to sustainability in our cities, we can think that a city, to be sustainable, it must above all be safe against natural hazards related to climate change, but also to seismic events. So I thought it was so important to take this into consideration with my work, because I have in the past only focused on energy efficiency and thermal comfort and passive house, but now starting to look more holistically in terms of retrofit, because there are so many other factors involved in a retrofit project. So starting to think more broadly, how can we integrate things a little bit better in a retrofit project? So how did I get to this idea of working with unreinforced masonry buildings and working with heritage? I started thinking about how so many buildings need energy retrofitting in Aotearoa, so it's like really overwhelming. Where should we focus? Where should we start? If we think that most of our building stock needs to be retrofitted in future years. So I started to look into which buildings will certainly be here in future years, which buildings we really need, we really want to keep for future generations, and that's where historic heritage came into place. And then also which buildings are already going through major renovation at the moment. And that's where the seismic strengthening side came into place into the research, because I was just noticing how so many major renovation projects were taking place all around Aotearoa. They were upgrading the structure of these buildings and also some other aspects, but they were really missing key opportunities. So I would see things like this major renovation project where single glazing was being replaced with new single glazing. Or they had this major renovation thinking about the structure of a facade, but without making any improvements to air tightness or insulation in doing so. So connecting those two things together, I decided to focus on those buildings, unreinforced masonry buildings, because they are such a vulnerable construction type in Aotearoa. We know the impact of past earthquakes, especially in Christchurch, and so many issues related to that side, but also that they have such a poor indoor environmental quality performance and such a poor energy performance. So I thought that would be a good place to start to think about how to improve our heritage, that will be, we want to be here for future generations, and we also want to adapt it in terms of climate change. So the research really takes three key different areas of knowledge that are usually seen very separately. So looking at energy efficiency, and that's where EnerPHit comes into place. then integrating also heritage conservation and integrating seismic resilience. So that's the main opportunity that I found, was to work with those buildings that were already going through major renovations all around New Zealand. There are approximately 10,000 earthquake-prone buildings that will be required to be strengthened. So there's a mandatory requirement by the New Zealand government, and about 2,000 of those buildings are built of unreinforced masonry construction. So we really need balanced structural interventions, and we really should be thinking about integrating other components to start to future-proof this building. So that's where EnerPHit would be so important in this project. So there are certainly some cost considerations to think about that would really make sense in integrating seismic and energy retrofit. So once you have a major project in place, you have all the scaffolding, you removed all the tenants from, or the occupants from the building, you have this really huge construction team in place. So once you're doing all this work, then it really makes sense to add your energy retrofit to this major project. It's a very different conversation if you think about this, comparing to just simply talking about a starting an energy retrofit project where there is no need for major renovation for other reasons. So really starting to think about where we can take some opportunities in major renovation projects that are already taking place in New Zealand. So the main idea of the research was to integrate energy upgrades in current seismic retrofit projects. There was no data about this in New Zealand and very few examples overseas. So that was the key innovation of this project because not many researchers or practitioners had looked into this integrated approach before. And the research had many steps, and I'm just going to focus on a few of them because, of course, I don't want to take too much of your time. So I'm going to talk more specifically into 3 case study buildings that were part of the research, and where we took a comprehensive energy audit and understood the current performance of those buildings, and started to think about what interventions we could start to be doing and how you could build this energy retrofit project over a long time frame. So these are some of the key parts of the methodology that I'm going to talk about today. So these were the 3 case study buildings that I chose to work with. They were all university buildings located in different climate zones in Aotearoa. This is now an outdated climate zone map, as we all know, but at the time of the research, it was still the current climate zone map. So we had a range of different climatic conditions to work with, but a similar use in all of those buildings and similar construction. They all had unreinforced masonry walls, uninsulated walls, uninsulated ceilings, single glazing in all the windows, and some partly insulated roofs. So there was a comprehensive energy audit of these buildings, understanding the current performance, because again, there was no data about this in New Zealand. So just to prove that these buildings perform really poorly was one major thing we had to do in the PhD, something that it's quite obvious, but there was just no data to prove that. So very obvious things that we found when visiting those buildings was to see that people were bringing in lots of personal heaters to those buildings, as we can see in this photo on the left. And they were feeling really uncomfortable and cold in winter. Many desks just had heaters that people brought in, a very inefficient and uncomfortable way of of dealing with indoor environmental quality. So, and then we looked at thermal imagery with thermal cameras looking at facades and mainly the roofs where we did have some insulation. And we found some interesting issues, such as in this building where the ceiling was only partly insulated and the insulation package was just in there. It was just not installed. So someone did not a very good job, just did half of it and nobody knew about it. So just some very simple problems that we could solve. But of course, then we go more deeply into what would be the ideal way to retrofit a building. But just in general, a very obvious results was just showing the very poor performance of those buildings and the poor quality of the insulation installed in those roofs. So again, here talking about indoor environmental quality. So a lot of complaints both in winter and in summer. People saying it was very, very hard to work in these environments, falling asleep because it is so hot, and then also feeling very, very cold in winter, especially in the cold winter mornings. So obviously a lot of areas for improvement, both in terms of energy efficiency and in terms of thermal comfort. So based on those issues, we developed a few retrofit scenarios that we could work with. So starting from a baseline, the building as it currently was, then looking at seismic strengthening of this building only, so only adding the structural elements that were required to be added as part of this seismic renovation work. Then we started to look at adding roof and underfloor insulations, just some of the most common interventions that we have in this kind of building. Then what would happen if we started to work with upgrading windows and air tightness? And in here it's very important to mention that there are so many options for window upgrading. And overseas, there were many examples where you keep the original window and you just install secondary glazing either on the inside or the outside. So that was one of the key findings, that in New Zealand, this was not really common practice. We were either talking about finding examples where windows were left just as existing, just as the original ones, or they were being completely replaced. So we were really interested in looking at these examples where you could really have a more sensitive approach, where you keep the existing heritage and you still improve the energy efficiency of the building envelope. And then lastly, looking at adding heat recovery ventilation, and finally adding wall insulation, which would be a more impactful intervention in terms of the heritage and what is visible on the inside of those walls, but that certainly makes an impact in terms of the energy performance. So I started to look at the structural elements in these buildings, looking at what was proposed by engineers who worked on those retrofit projects. So structural elements were taken as a fixed factor. We were not really proposing changes to the structure, just taking what was done in those retrofit projects, and then starting to integrate with what could be done in terms of insulation, air tightness, window upgrades, etc. So the modeling was done in PHPP and also in WUFI for hydrothermal simulation, and the results showed that it was really possible to achieve significant savings when you go from the baseline to the last retrofit scenario, which includes all those elements, including wall insulation. We achieved up to 90% reduction in heating demand, comparing scenario 1 to scenario 6 in the case of Dunedin, the coldest climate that was studied. So that was the energy side. So it was just understanding what was the potential savings that we could get if we applied all these interventions. But then how do you balance the heritage side, the historic building fabric, and how do you make the interventions in a way that is really sensitive to that heritage, that you're not changing too much of this existing building and the existing facade? So to do that, we worked with this guideline from Europe called Energy Guideline for the Energy Improvement of Historic Buildings. And this was really looking at the benefits and the risks of each intervention. So what would actually be feasible and what would be really recommended for each building. So it's just really talking about a balancing act that we might see that this intervention would bring a lot of energy savings and benefits in terms of comfort, but what would also be the downsides in terms of the heritage impact. So quickly looking at some of the conclusions, the research reviewed some of the obvious issues that we knew were going on in unreinforced masonry buildings, significant issues in terms of energy consumption. Some of the buildings consumed up 40% more energy than similar buildings in the same university. So it was really, really high energy consumption with still providing a very poor level of indoor comfort. The satisfaction with the internal environments was found both in winter and in summer. So that's a really key aspect to think about, that we're not just thinking about improving those buildings in terms of heating, but also in terms of cooling, thinking about future climatic conditions with climate change. So the research also showed that it's possible to improve the building envelope in URM construction and achieve significant savings in energy and especially in heating demand by using the EnerPHit standard. And this is especially beneficial if we integrate EnerPHit with another standard that really works with historic buildings. So EN 16883 is really great to inform this decision-making process. The energy models in PHPP demonstrated a reduction of up to 92% in heating demand when we compared at the baseline with the most comprehensive retrofit scenario. And this would ensure achieving the EnerPHit standard in that case. However, we should still consider the impact on heritage. So this research was not just about achieving EnerPHit, but also trying to see where it would make sense and where it would make sense to have fewer interventions or some interventions that don't have a significant impact on the facade and on the existing fabric. Then hydrothermal simulations showed that some key materials such as perlite boards and calcium silicate boards achieved the best results in terms of hydrothermal performance. So we looked at those intersection condensation risks. And I don't have time here to talk much about that, but I can send you some more information if you emailed me. But there are some really interesting materials being used overseas to be able to deal with this issue of insulating from the inside in historic buildings. Right, and it's really working with retrofits in historic buildings is really about having this balancing act where you have all these key disciplines and all these very important factors working together. And it's really important that teams work together and ensure that all these voices are heard in the design process. And having this integrated approach can really help to improve the resilience of these valuable buildings and ensure that heritage buildings can continue to serve a useful purpose in a post-carbon future. So really thinking about what we leave for our future generations. So certainly we want to leave a better planet. We want to leave a low carbon future for our future generations, for our children. But also we don't want to lose history as well. So we also want to leave this heritage, these beautiful buildings that are part of our history. So I believe we can leave both things, and we can really work in adapting these buildings so they can continue to be used by future generations, and they can be a part of the change of making things better for our future. So that's it for me for today. It's a really, really long research project, and these are just a few key areas that I thought would be more interesting to present today. Thank you very much, and I take this opportunity to thank everyone who helped in this research: supervisors, the University of Auckland's funding, advisors, and also the Passive House community that is always very supportive in New Zealand. Thank you.
Thank you, Priscilla. That was very, very interesting. Oh, I know you have to go, Priscilla, so I won't keep you. And please tune in again, onto our website if you want to watch the rest of the session. Thank you, Priscilla. Now we're introducing Daryl Sang from Sang Architects, who's going to talk about an EnerPHit case study. It's the Piha House in Auckland.
Good afternoon, everyone. Let me just turn on my screen sharing. Here we go. Can you all see that? So yes, I'm just going to do a presentation just about our EnerPHit project out in Piha. It happens to be New Zealand's first certified passive house EnerPHit. We're very proud of that. It's been quite a long journey and quite a lot of work. And I think Priscilla also mentioned that it's a team sport, and we had a great team to be able to accomplish what we were able to do, including the client, who was extremely committed. So let me just quickly summarize what I'm going to talk about, and then we can get into it. So yes, I'm Daryl Sang from Sang Architects, and yes, I'm talking about our Piha house renovation. I'll first just talk about the motivation for the client and its brief, and just quickly run through the site the house is on, what the design specification was, and run you through the construction methods we used and some of the materials, and then a few completed photos. And then hopefully will be time for questions right at the very end. So as I said, I'm Daryl Sang from Sang Architects. We're registered architects, and I'm a certified passive house designer. And our team at Sang Architects, we have 2 certified passive house designers on staff and a couple more working their way through that. And our mission is to be totally passive house. So onto the Piha house. It was the renovation of an existing concrete house built in 2008. So quite a bit more modern than some of the buildings that Priscilla's just been talking about. Quite a large house, 345 square meters, with an additional 70 square meters of terraces. Being all concrete, and it was actually a concrete mid-floor. So we had a lot of issues with thermal bridges where the concrete internal floor flowed straight out onto the concrete terraces, and below some of those terraces we also had habitable rooms. So we had a lot of issues with internal moisture and condensation. Building is 2 stories with 3 bedrooms and 2 bathrooms. The original brief was really just to up-spec the building. We were going to put in new kitchens and bathrooms, change the existing window joinery from single glazed aluminium to high performance windows, and add a guest bedroom. And improve the air tightness. But during the initial demolition, when we opened up the walls, we found mold almost everywhere in the building. And this is what prompted us and the owner to take on a full passive house EnerPHit renovation, because the client had some health issues resulting from years of living in damp, moldy homes, and that drove his desire to do the full EnerPHit renovation, so we didn't get any mold or condensation again. So the site is quite a big site on the hill just above Piha. It's 104 meters above sea level and very high wind zone. Faces northwest, so you can see our site here on the right hand side, and the views and down to Piha, that's Lion Rock there, are west. Again, that's the site there. And let's just have a quick run through the specification. As I said before, it was a complete concrete house, concrete blockwork walls, ground slab, suspended mid-floor concrete slab with terraces, and again, just standard aluminium windows, simple glazed, and I had a very bare minimum insulation on interior. I only had 25 mils of polystyrene and some fiberglass bats in the cold roof, timber roof with a rubber membrane on the top. And we were retaining the existing concrete structure. We put in high performance smart windows, and we went for a Stotherm external insulation system, where we put insulation and plaster on the outside and changed the roof system to a NeuroPly warm roof. And again, did the new kitchens and bathrooms, add the guest bedroom, had a Wolf MHRV system with an extra dehumidifier for the damp Piha air, and a heat pump hot water cylinder. And we also put solar PV on the roof. And it was, we're collecting rainwater, and we had a water bore, and also, opening and louver roof to provide shading and shelter on the west-facing deck. So again, that's the house on the site. And I'll just quickly go through this plan. So this is the ground floor. Main entrance is right in the middle. We had a couple of bedrooms downstairs. This end bedroom was actually underneath one of those concrete terraces. That's the main garage. And then this was, this is where the guest bedroom was installed. This was previously open underneath the external concrete terrace, but we built a new room underneath that terrace. And upstairs is the master bedroom on the end. That's that external concrete terrace. And then the main living area and kitchen here with, again, another concrete terrace out here. And this looks kind of west out to that view of Lion Rock. And that's the roof plan. That was initially the existing rubber membrane roof, and we converted that into a warm roof. And as I mentioned before, that these projects are a team sport. There's a lot of input from a lot of different consultants and suppliers and contractors, and it needs a great deal of commitment and coordination from all parties in order to get the project to come together, particularly with the EnerPHit. It's part of our team. It's the builder and the client on the right, Bjorn Hilke and Janice Al from our office. And that's the team again, and me on the left. So let's just quickly go through some construction photos, just showing where what we had to do. This is the house as existing. though the builder at this point has started to strip things out. And you can see we're dealing with just plaster on blockwork and a lot of cantilevered roofs and kind of awnings over the front door. And that's all that single glazed aluminium joinery. This is the back end where we've already taken out the some of the aluminium joinery upstairs, and that's that concrete terrace where we built a guest bedroom underneath it. So this is just taking a step back. This is that main living room area before we did the strip out. Just things to notice is that it's the single glazed aluminium joinery. We had a lot of cedar louvers for ventilation, but of course they're very poor air tightness, so we had a lot of drafts. Extremely cold in the winter, very hot in the summer. This is after the strip out. So we took everything back to the original structure. That roof above, that's a timber frame roof with steel supports, and some of those steel beams, all of those steel beams actually cantilevered out through the thermal envelope and supported the eaves. And also most of the timber structure also cantilevered from the inside to the outside. That was a cold roof. So when we had a good look at the roof interior, what we found is, this is looking up into the roof. This is the ply on the back of that rubber membrane. You can see the white mold forming in that roof cavity. That's exactly where you'd expect to see it. You know, down here is where this was below the gibboard ceiling. And so those downlights you might have noticed in that previous photo are completely open into the ceiling void. So all that lovely, warm, moist, humid air comes up into the ceiling and rises to the coldest point where that's the back of the uninsulated rubber membrane, you know, passes right through the fiberglass bats and then again just condenses in the coldest point. We found that right through, that mold right throughout the whole building. This is the master bedroom, and you can see the black mold staining on the cantilevered, I think these are plywood LVLs. And you can see those plywood LVLs cantilevered right outside through the exterior envelope all the way to the outside. And you also notice this is daylight through here, so the soffits were completely open to the roof cavity. So lots of cold air looking up in that roof cavity. And of course, after you've stripped off some of the flashings, we saw there's a lot of mold, moisture damage to some of the timber on the back of those metal flashings, just where you'd expect all the condensation to form. And on the exterior blockwork walls and underneath those concrete terraces, maybe a bit hard to see in here, but just along the top of the wall, you can see that's the coldest point where that heat's been sucked out of the wall up through those concrete terraces. And you notice that kind of staining there. That's where all the condensation and mold was growing on the surface of the block. So when we found all that, and given the client's health history, we decided to completely treat the inside of the building with a relatively environmentally friendly fungicide. So that was completely sprayed right throughout the whole house to treat all those surfaces, kill all those mold spores. And then the entire inside of the house was sealed with a I think acrylic sealer just to encapsulate all those mold spores. So we had to deal with all the air tightness. This is lots and lots of taping to all those junctions where the structure was cantilevering out through through that thermal envelope. Lots of taping, and you can see here, this is a steel beam that cantilevers from the inside of the building to the outside. Again, that was taped and had external insulation put on the top of that. And then we started sealing up that ceiling cavity. We use Intello as really a vapor restrictor. And you can see that the green MHRV piping going in, and also the extra heat pump air conditioning units for that summer cooling. Quite a process to do that. This is the ceiling going in, and quite a high spec finish. We've got cedar on the ceilings and special European birch plywood linings on the walls. And this is kind of coming to the end where the client's starting to move in just before everything's completed. It's that brand new kitchen. This is taking a step back. This is actually showing condensation forming on the underside of those concrete terraces. This was when the house was completely sealed up with that white acrylic sealer. This actually stopped moisture penetrating into the porous concrete. And so what happened is when the house was left out in the cold with all the windows had been taken out, concrete structure would cool down to such an extent that when the warm morning breeze came through, that warm moisture came and met the cold concrete structure and basically formed rain droplets. It started raining inside the house. Normally you wouldn't see that because that condensation would be absorbed into the concrete, but because it was sealed, we had a very good indication on what that moisture load was like. So some of these terraces we couldn't insulate on the outside, so we insulated the inside. Jason Quinn had to do a lot of thermal modeling for the thermal bridges, and we insulated the top 600 mils of those the concrete walls, because that's where they were the coldest bit, where that heat was being sucked out of the top of the concrete walls by that cold concrete terrace. So that's showing that internal insulation. And again, after the finishing, there's special ventilation paths above the ceiling. I'll just go back. This is kind of a labyrinth formed in the ceiling with vertical bits of insulation. So the air can get removed from the room and it gets sucked through as kind of a zigzag path and out through the extracts. So we can be sure that those ceiling voids are ventilated just in case any condensation does form because of that internal insulation. And just quickly on to the roof. That was the original uninsulated or cold roof with that rubber membrane. We had to increase the pitch on the roof and then put in 2 layers of the insulation board, and then a whole torch-on rubber membrane on the torch-on kind of Neuroply membrane on the outside. And we installed thermally broken fixing points for solar panels. At the time of all these photos, the solar panels weren't installed, but following these photos, we had something like 30 solar panels on the roof. And just quickly, external insulation. We couldn't get under the slab to add more insulation, so we added edge insulation. And you can see the edge insulation down there at the bottom of the wall. And then added, I think it's 100 mils of neopore carbon impregnated insulation. On the outside, that's the stove-therm system. All those insulating panels, you can see the white circular thermally broken fixing points. And that's the final plaster system going on the outside. Again, quite a labour-intensive job. This is up on that west-facing terrace that faces down at the Piha Beach. Again, you can see those soffits that we had to do all that air tightness taping on, and lots of taping around the new windows. And that's that thermally insulated plaster system going on the outside. And that's that external louver roof, which aided the shading. This deck and all those sliding doors faced almost due west, so a massive big heat load. We'll just take you through a few of the final pictures on the site. Here we go. I know we're just coming up to time. So a very high standard of finish, and all credit to the builder and the construction team. It's Terry Bryers of Brewery Limited. Did just an amazing job. And really, you know, we are passive house designers, but we're also registered architects. So the architecture is just as important as the overall performance. So thank you, everyone. That brings me to the end of my presentation.
Thank you, Daryl. Really appreciate that you can join us today. We're going to go to introducing the one and only Jason Quinn from Sustainable Engineering, who's going to talk about low carbon refits in New Zealand, EnerPHit by the component method. Over to you, Jason.
Oh, thank you. Let me see if I can get this to share properly. I'm a registered professional engineer. I should be able to push buttons on Zoom, right? That's how it's supposed to work. So we'll see how that goes. Has that started sharing yet?
Not sharing yet, Jason.
Certainly hit the button a number of times. We have to send my slides to Daryl next time so he can drive. All right, I'm gonna fail and rejoin perhaps. Is that the recommended process? Because I've got the sharing button up and I've clicked it a number of times. Oh, there we go. Is that sharing now?
Yes, that is sharing now.
Thank you for small favors, as it were. All right, cool. So my name is Jason Quinn. I work for Sustainable Engineering, and I was lucky enough to get to work on the Piha project that Daryl just spoke about. I would like to make one point is Daryl was quite rightly thank the builder, because the builder spends the most time on the site, and they're really critical, well, probably the most critical person to a successful project. So I was the pass house designer on that project, but the reality is the architecture team at Sang Architects did a lot more work than I did, and we're a lot more critical to its success. So I'm lucky I get to play with mass. And so on this particular project, I'm presenting, but actually the majority of the research work was done by Toby Brook, who works in our office. And he's done all the embodied carbon calculations and a bit of energy modeling. YRO is one of his projects. He's the pass house designer for that. But with that, I'll just get into it. So if we go down to the next slide, sweet, the buttons work. So we've got here the EnerPHit. When we talk about EnerPHit, and Daryl's talked through that, most people think about, and in Priscilla's presentation as well, people think about this energy demand method, which is on the left. So what I've done is I've color-coded the map of New Zealand for all the different climate zones at the weather station altitudes. It does change slightly with mountains, and put down what the EnerPHit targets are for the different heating demand for those things for EnerPHit. And you can see in the warm climates, in Auckland in particular, it actually matches the passive house requirements of 15 kilowatt hours per square meter per year, which means for an EnerPHit project, you're actually if you're trying to qualify as an EnerPHit project by strictly hitting the energy demand, the heating demand, you're actually designing a passive house. Now you do have a bit of more allowance for things like air leakage. You can leak about 40% more air than you can for a certified passive house, but the requirements are very similar. They're just as hard. And that's because for a heritage building or an existing building in Auckland's climate that is well oriented, you probably can get there quite easily with the energy demand method and hit the passive house criteria because the climate's fairly benign. However, passive house institutes realize, because they've done lots of buildings around the world, that that's not always practical. You can have a building in a climate that's very similar to Auckland. We have an example here in a few minutes. We'll look at some case studies that cannot meet the EnerPHit energy demand method with even passive house level enclosure, like put in passive house certified windows for even a cold climate, put in very thick wall assemblies that would easily make a brand new house be a passive house. And it won't work in the retrofit because it's got very poor orientation, or it's got a really ugly form factor, or various other reasons. So in the standard, in the passive house certification standard, if you read it, there's also this thing called the EnerPHit criteria by the component method. And what's supposed to happen is you aim at the energy demand method when you do your EnerPHit models. And then if you can't get there for one reason or another, you go ahead and use the component method to get there. So we'll look through several examples of this in a few minutes, but ideally, kind of thinking about it with the PHI project in mind for a moment, we aimed at the energy demand method. But if you look at the certification certificate that Daryl proudly showed earlier, you'll see that there's a higher than 15 kilowatt hours per square meter per annum for heating load for that building in the passive house planning package model. And that's because well, one, we get an exemption for the slab, and we'll talk about that in a moment, but also because we switch from aiming at the energy demand method to the component method because of the building's poor orientation. Is really what it comes down to. So when you're looking at a retrofit for EnerPHit, realize that you want to start by aiming at energy demand and design your enclosures to hit that. But when you hit a point where it doesn't make sense, you want to switch over to using the component method. And even that, when you get through the component method, and just so you know where the component method stuff is, when you're using the passive house planning package, there's this little plus, well, it's shown as a minus here, but it's a plus when it's not expanded on the left-hand side of the verification sheet. And you can click that once you've got your building entered into the PHPP, and that'll drop down the EnerPHit component characteristics. And it'll show you what you're actually achieving in your building with your current inputs, as well as what the requirements are for that particular climate zone. And that's what's shown up here in this criteria here. These are the requirements for each of the 3 climate zones in New Zealand. The one here in gray to ground is actually calculated specific for each building. So it's actually customized in PHP. All right. So that's where you can get the EnerPHit by component numbers, first of all. And it seems like a lot of folks don't know what those are. I know I've heard Cara Rosemeyer, when she taught that class, I want to say it was a decade ago now. I do remember her talking about retrofit as being the black belt sort of passive house design. And it can be that to some extent. And part of that black belt is realizing that there's not only the energy demand method, but also the component method, right? Now, on top of the component method, there's also step-by-step EnerPHit. And you can do a step-by-step EnerPHit for both the energy demand method and the component method. Now, Priscilla didn't get into this when she was doing her upgrades, but she used the step-by-step methodology. She had a note on her slides. And she looked at that to look at retrofitting in stages. In other words, to look at interventions in her heritage buildings. But the reality is that you can also look at it in a single building. And we'll do that in just a few moments, right? Now, in addition to this somewhat complicated sort of scenario we have now, we've got EnerPHit by the energy method, EnerPHit by the component method, and either of those you can do by either all at once or the step-by-step approach. All right. If you do the step-by-step approach, you design all the way to the end. That's what you want to do, just like Priscilla did in her slides. But you can go ahead and stop after a certain number of steps when you've hit a certain level of energy efficiency or carbon reductions by PER reductions, and get pre-certified. So you can get a pre-certification plaque. No one's done that yet in New Zealand, although we've got one project that I expect to do that shortly. That reason for that is that you might choose to do you might choose to do an EnerPHit project on a building by the step-by-step method, and you're going to have that carried out over, let's say, 40 years by the time it's finished. But so by registering that entire EnerPHit plan with a certifier, it goes on the online passive house certification platform, and that's intended. It was actually developed for the step-by-step EnerPHit approach. Is that you might retrofit the first step now or in a year or two, but the other steps might only occur when that parts of the facade need to be done. Right? On top of those two, or I guess there's 4 strategies there, there's also these EnerPHit exceptions. And you can read them at length in the certification criteria. I don't want to go through them at length, but they're for practical limitations, and don't do stupid stuff. Because although there are exceptions, they're not a carte blanche, so they're not the right of the designer. They're actually, the practical certifier would look at them and say, no, no, you actually could fix that, and you are actually required to fix it. I'm not going to let you have that exception. So don't do stupid stuff. That's what it comes down to. And I'll show you one exception which PHI granted on a project I designed, which is the one we just looked at. So this is a project that Daryl just presented. As I said, I was the pass fail designer on it, but I did, relatively speaking to what Janice and Daryl did on this project, a very small amount. And of course, even then, of course, we did very small amount compared to the builder. So it's a beautiful building, as you just saw. And Daryl's gone through all the constructions, so I can actually skip going through that. What I will show you though is the graph, right, of the numbers, as it were. So this is the monthly energy balance for the building over the annual year, but it's a monthly method one, so it's the accurate one. And if you notice, it says 27, not 15. And the reason that's still a certified pass-faust EnerPHit, certified EnerPHit, not pass-faust. It is a PHI EnerPHit building. The reason it's certified with the 27 there in Auckland's climate is that it's been done by the component method. And over here, I've shown the retrofit characteristics from the PHPP, and I've opened it up, and you can see that the building envelope to ground is 5 watts per meter squared Kelvin, or an R value of 0.2. Whereas in reality, the EnerPHit criteria, if you're going to do the component method, requires 0.92, which means it does not meet that, even the component criteria. So as an exception applied in agreement with the certifier, basically we weren't going to insulate the skirt because it was a concrete mid-floor and a concrete ground floor, and there wasn't sufficient height to put insulation on top of the slab and make everything work. So we added an external skirt. Luckily, I don't need to go into that too much because Daryl's already done that. So this is one of the case studies we'll be looking at as we go forward and look at embodied carbon. All right. The next case study we're looking at is not been started yet, but this has been through pre-construction review by PHI again. So it's been all approved. If we build a building per the drawings and pass our quality assurance checks, then it will be certified as an EnerPHit project as well. This one, the architects are Cloud Project Studio. So Matteo and his partner there at Cop Studio are the designers for that, architecture people. And then Toby Brook is the designer for this project for the pass-faust design. And this project, sorry, Daryl, is all internally insulated. The advantage this had over the EnerPHit PHOT project is that there was no concrete mid-floors, and there was only a short stub of a brick wall that was inside, because this is a historic brick masonry building. It's 100 years old, although it's certainly not in the architectural list. The entire brick envelope is being preserved. The existing roof is being retained, and this will be retrofitted to an EnerPHit quality space. We'll look at the graph in just a sec with PIR foam floor, 2 layers on top of the slab. Black EPS foam, the same as you saw that neopore on that Daryl showed us on the outside of the building, is now going inside of the external walls, and then Intello and fiberglass on the roof, right? And then windows pulled back into the insulation layer, right? So if you look at the graph for this project, again, it's all the way up at 36 kilowatts per square meter, way over the 15 that's allowed for the energy demand. And that's because it's meeting the component method. In this case, we originally had an exception from our certifier to use double glazed UPVC windows for local manufacturer, but a importer with triple glazed windows, relatively low performance triple glazed windows, has come forward, and we'll be using those in this project. At least that's been approved through pre-construction. And the sky is just squeaked under the component criteria, but we had discussed potential for an exception for that. So this project right now has been through pre-construction with no exceptions, because if you look at the component characteristics, it meets all the component criteria throughout the project. And we aimed as closely as possible at the energy demand. But the reason it has twice the heating energy demand of the requirements of the energy method is because it has extraordinarily poor orientation, very little glazing, almost all the heat gains through the skylights. So it's the few windows does have a facing the wrong direction for solar heat gain. So that's an example of a very practical approach for EnerPHit. And this last one is a EnerPHit project in Jester Street project. And this one is a roughly 100-year-old timber frame sort of villa, railroad structure house. And this one is being done by step. We're targeting the first step, and the windows are going in Monday, actually. So the first step of this is being done, which is the owner switching over to triple glazed windows, which will be ready to do all the way through EnerPHit. They've replaced all the gas systems with electric, switched to electric heating and cooktop and such. So the next steps, which I'll show you in just a moment, include external insulation, insulating under the floor and adding an air control layer. Currently, right now, the plan for that step, which is potentially very far in the future, is to spray the underside of the existing timber floorboards with Viscon to create an air control layer, and then using batt insulation and a wind wash membrane. It's very difficult to get under this house. There's only about 220 underneath the joists to get squeezed under. And then, of course, in an MBHR at that point. So how do you know when you do a step-by-step? This is from about a month ago, where one of the windows literally fell out of the building because they're all, well, they're not all, but almost all of them are rotted and have had their useful life. So that's definitely time to replace the windows. So the way it'll work, and this is the step-by-steps, this is the EnerPHit retro plan page. You use the variance feature in PHP, and you can calculate, and you basically put the original building in and then put in various upgrades along the way, all the way down to you meet the standard, as it were. So the first step is to upgrade the windows and, again, take out natural gas, and that should be sufficient to do to target pre-certification with PHI, and that's the intent to do that, right? And there's other steps. And again, this one will meet all the criteria for this. There'll be no exceptions targeted, or at least there's none planned at this point. And the biggest challenge in this building will be the air tightness target in some future steps. And here's the graphs. If you've not looked at these graphs before, the variance, the losses are just shown downwards instead of two vertical columns as previous, right? And you can see that even in the final step, the heating demand is almost 60, because again, it's poorly oriented with very small glazing that's very well shaded. It's an existing building. So the only approach that can make sense is to aim at the component approach. And again, we've looked at using PASFOS level of assemblies for this climate, and then use the component approach to make it a practical step. All right. Now, the reason we have these three case studies, and I apologize for not being a super presenter and explaining that before we even start. The reason we look at these three case studies is to look at the embodied carbon in them, and to see if EnerPHit really makes a sense in New Zealand climates as we stretch it across. So I'll spend this last few minutes talking through that. So skipping through the methodology, and this is all work that Toby Brooks done, by the way, modeling all these. We modeled both the operational carbon and the embodied carbon based upon, at least to our knowledge, the best practice in New Zealand at this point. So following the embodied carbon, following MB's technical guidance, which still has some complexity with that. And that means that the embodied carbon is looking over 50 years for the building instead of the 90, which we would have used just 6 months ago. And then for the operational carbon, we're modeling the energy consumptions and such in PHP with the grid factors from MFE, which have then been tweaked by brands to make them slightly worse to account for some other losses that are in the system that aren't in the MFE tables. And I guess the only other point that's real important for the operational carbon is, although the building is modeled in PHP at 20 degrees, we change it to an 18-degree balance point to match up with the other embodied and operational carbon calculations that are being done around New Zealand. All right. Okay. So doing that, we end up with these graphs that look like this. And I want to explain the graph because I want to flick through quite quickly through the rest, because you can get the point from just a few of the graphs. So you have this purple stuff, the green stuff, and the green stuff is the embodied carbons for A1 to A5. In other words, everything through handing over the building keys, right? And then the purple stuff in this core here is the embodied emissions during and beyond operational use. So that would include things like maintenance cycles, replacing windows, replacing facades, painting facades, that kind of stuff. And then the red stuff up top is the operational emissions for electricity and water use and that kind of thing. And then because you can have both positive and negatives in several of these, certainly in embodied energy, you can have both the energy required to build a timber wall, as well as the carbon that's stored in that wall. Both the positive and negatives are charted on this plot, and then the total is shown with this little yellow bar. So we're now going to look at this building here, which is the PHA building. So this is the existing building's both operational and embodied carbon. So that's why there's no purple, because there's no initial construction, because it's the building as it currently sits. You can see it's very high operational energy for heating, even at 18 degrees centigrade, and even with the reduced grid factors going forward in time over the next 50 years, right? And then we look at our current New Zealand H1 building code building, and then going forward all the way to the planned EnerPHit approach. Right? And then the slight less heating, but more embodied carbon. That would be if we'd taken that particular PHI building and just said, screw the cost, screw the construction complexity, and made it meet the heating demand. If we did that, if we just forced ourselves to, actually in this case, we'd have a worse building. And that's one of the conclusions we'll get to in a minute. And looking now at the Wairoa project, again, we have kind of the same approach. We have the existing building with a ginormous heating demand, even at 18 degrees centigrade. And then if you jump it down to all the way down to the planned EnerPHit approach, you can see it's very small. Right? Yeah, I think that's probably the approach to look. There is, in this one, if we pushed it all the way to EnerPHit heating, we'd get a slight reduction in the overall carbon emissions from 48 tons to 46, but it is that there. In Jester Street, again, a fairly similar story, except this one, if we pushed it, yeah, a very similar story. You get this huge demand initially. So you can see where in this case, the greenest building is not the existing building as it is. It needs to be reduced because the heating energy alone in that existing building vastly outweighs the embodied carbon that needs to be put into the renovation when you look at the additional difference you have for having that energy efficient. And this building, certainly they need to replace the windows regardless, right? They're literally falling out of the building. So it needs new windows, so you have to put some additional carbon in, and that's what's going across here. All right. Now, if we take these 3 case studies and run them all around the country, you can see that obviously the carbon emissions go up, but it is not a hell of a lot required in the purple, which is the additional embodied carbon to make the building work. And the same thing for the Wairoa project and for the Jester Street project, which is Timber One, right? You're putting additional embodied carbon in the structure as you add additional structure, but the total carbon emissions, both embodied and operational, including maintenance, renewal cycles, facade, and everything else, is actually staying relatively flat as you go across the different climate zones. So you're putting more carbon in, but it's balancing out the same because of both the pluses and minuses in the materials. Right. So stepping on the last few minutes to conclusions from all those charts is that deep retrofits should target EnerPHit heating demand. Put in what seems like when you start doing the component method, seems like crazy good windows, because you can replace windows entirely. Sorry, Priscilla, except for when you have to, well, you can still put in crazy good windows. You just put them behind the heritage windows in those heritage buildings. The component methods and exemptions or exceptions built into the certification criteria are designed to make it practical and economic. And if you look at some of these charts, you can see that cost and carbon often line up if you do it right. When you're doing EnerPHit retrofits, don't forget about hot water use, plug loads, and maintenance requirements. And we don't have time to go through this nice story about Kangaroa and their choices on the Nakanga Anamata project for claddings, but that had the lowest, very fancy cladding had the lowest life cycle costs. EnerPHit is achievable and close to best practice, best possible approach, but also has this practical step back using the component method, and if required, the exceptions built into the certification criteria. If I was going to try to summarize the whole summary in one, to be aim at the energy target EnerPHit for all of our retrofits in New Zealand with really good windows. All right. In big picture, if you're taking a step back from just looking at this particular presentation, New Zealand needs deep energy retrofits. They do make sense from a carbon point of view. Unfortunately, we've kind of already blown the 1.5 degree budget, the 35-ton budget we've seen published before already with our current construction boom. And we're going to need to get really deep retrofits to have net zero by 2050. Our choice for existing homes is basically have them unheated and unhealthy like we have now, or to fix damn things. With that, we'll step back and stop sharing.
Oh, hang on a second. Thank you, Jason. Thank you for that. Absolutely delightful to have you here today. I'm just going to go to some questions. Oh, just waiting for Daryl. Oh, there he is. Okay. Some questions. Is there any effort to think about large-scale energy efficient retrofits in New Zealand buildings, similar to the energy sprong idea in Europe?
I've certainly talked about that with some folks at Kangaroa, but not really is the bottom line. I mean, Kangaroa is looking at retrofits, but not like Energy Sprong does.
Right, thank you. Jason, is that heat balance graph with gains above the line, losers below the line in PHPP variance, or have you created that?
So variance, ooh, that's a good question. I certainly created that particular graph. I don't know, actually, sorry. It's been so long since I built that graph. I don't remember if I did it or PHI did. It's certainly based on something PHI did. It certainly wasn't my idea. So I'd like to say it's somewhere in variance, but maybe not. Sorry.
Right, here's another one. Emissions seem to be a significant part of the total carbon emission in the graph. Can you explain this?
You mean the red part, which is the emissions from operational use of the building, is a significant part? Yes. So when people look forward to a fully renewable grid has a hell of a lot of carbon emissions, right? Just because you have a hydroelectric plant producing power, and at the moment you look at it, it looks nice and green, doesn't mean you didn't put a whole bunch of carbon in the ground with digging and concrete and building power lines and everything else. So even when we have a fully renewable grid, it's still full of a whole bunch of carbon sin that we've got to deal with. And so that's why, even with a passive house, if you've got plug loads and such, which you will, there'll still be significant carbon emissions associated with using electricity going forward. It's much lower than it is now. We've taken that into account in these calculations, but it is not a free-for-all in the future just because it's a fully renewable grid.
Right. Here's another question. I'm not sure what it's referring to. Can you make it work without super duper windows?
Maybe, but that'd be pretty stupid.
Mm.
Because you can already, like, that's the one component you're going to generally replace entirely. Only with Priscilla's heritage buildings would you do something funny. In that case, you would still put a brand new window in. You just put it behind the existing heritage window. At least that's what's usually done. So.
Jason, did you compare deconstructing Ingestra house rather than retrofitting it? If you use a lot of carbon negative materials, is there much point in keeping a really poorly orientated, poorly planned old house instead of rebuilding it?
Yes, personally I did. In other words, I had a long conversation as well as the passive house builder with the owner of that particular building, and they loved the building and told us to get stuff if they want it retrofitted. And I think Daryl could probably speak more to that than I can, that people fall in love with their homes, especially if they're well designed, and even if they aren't necessarily very energy efficient or comfortable. And sometimes they want to retrofit them regardless, even if it is cheaper to tear them down and start over.
Yes, I guess I have a comment just about the Piha house. I think there was quite a lot of effort and time and budget put into actually retrofitting that house. I think if we'd known that it was going to be a full EnerPHit retrofit from the very beginning, we might have suggested, economically it would have made sense, I guess, to actually start again and orientate the house right and give them exactly what they want. But I guess on the other hand is that there was a comment in one of the questions about embodied carbon and CO2 and versus the materials we were using materials that did have a certain amount of energy and carbon embodied in them. But I guess that's also balanced by the fact that we actually saved all that massive embodied carbon in that complete concrete structure. So I think there's pluses and minuses to all these things, and you really just need to make the best, most economical and sustainable decision you can at the time.
Yeah, I mean, so on the Ingester house, again, like Daryl was saying, the owner knows in this case where I've said it's cheaper from a whole cycle to just tear it down and start over. But the reality is that she's going to get a home that's much better than she has now, with triple glazed windows in it, and a non-gas heating and cooling system, and to use for 30 years or 20 years while she saves money to do the rest of the retrofit, right? Whereas if we were going to wait till the end, she'd have to live in the existing house with no windows because the windows are literally falling out. She'd have to, I don't know, staple plastic over my ass? Would be the choice? No, it would be silly. So she could replace them with cheap windows, but the cheap windows would cost 60 or 70% of what she's getting for the triple glazed, because she's getting locally produced UPVC windows out of Christchurch, NK windows, with triple glazing in them. So they're not, they're fairly economical actually.
Yes, that's one thing about stage retrofits or stage alterations. Yes, you get a great performing house at the end, but yes, just the alteration allows you to stage it as your budget allows, and allows you to keep using the building. Whereas if you go all the way from zero to the end, you're basically kind of starting again, and then you don't get to use the house while you're doing all that. So.
Yeah.
Okay, so a question for Daryl, I think. It's the same question. Do you have an idea of the dollar amount per square meter for EnerPHit, or what was the budget for the project?
I think it's actually a bit difficult to say for that, for the PR house, only because you could tell from the photos that the actual finish quality is very high, and a lot of the actual finish quality didn't have anything to do with EnerPHit. It was just the standard that they wanted. So I'm not sure of the split between what we had to do for EnerPHit versus what we did, because it was really a high-end finish. So sorry, can't really comment on that.
Right.
Yeah, the only thing I could say is the windows were about 35% more for the triple glazed UPVC over buying standard bog cheap double glazed aluminium. So that was an additional, what, is that 20K? So for the windows for that whole house, for everything, including all the French doors and including the front door being built as a reproduction, the existing front door. But the rest of the changes will happen in the future, hopefully when things are higher performance is more common.
Right, this is right. Don't you think it is more important to be savvy carbon emission than saving energy? Example, you can have a warm, dry house that uses very little energy through using high CO2 materials or CO2 negative materials. One of the reasons I think this is so important is that embodied emissions are imposed on the environment before the building is even occupied, whereas operational emissions accrue only gradually over time and diminish as our grid becomes greener. Do you have any comments about that?
So in New Zealand, we already have a pretty green grid. So our grid will get greener and we'll have reduced emissions from our grid, but not much. Overseas, that there's a big drop in the grid as it gets greener, because you've got countries that are burning a lot of coal. Australia might be a good example, where once they green their grid, there'll be a significant reduction in operational energy carbon per unit of kilowatt of electricity. But that's not going to happen in New Zealand because we've already got a very green grid. So I think what that person's trying to say is that if you build with carbon negative materials, is you can build to a lower energy standard and save on the embodied carbon up front, and then just pay a little bit more later, effectively, kind of like reducing capital costs and then paying more for energy along the way we do now with our current homes. I don't think that's a good approach, because the reality is in 2050, we have to be negative for the entire economy. So if you take a house right now and build it anything less than EnerPHit, or EnerPHit by the component method at the worst, then you're basically baking in for someone else in 2050 to figure out how to go negative. Because the budget for carbon emissions in 2050 for the whole world is 0. Not 1, it's not a positive number, it's gotta be 0. And likely is because we'll likely go over our budget between now and 2050, it's likely to be a negative number. In other words, we'll have to be spending resources to somehow capture carbon out of the atmosphere and land bank it. So it's going to be quite an interesting time. I'm lucky enough to be around to see it. So we'll see what happens.
And what do you recommend starting with for a step-by-step component method?
Whatever's worn out. So if you've got a building that's got a worn out roof, then do the roof first. It's got a worn out windows, which is this example, and start with the windows. And then of course, just make sure that each step you're not making the building worse. So if you decide to do the roof and floor, let's say, which were quite air leaky before, make sure you haven't created a problem with moisture problem inside the building, where you might need to put the MVHR in earlier on. But generally, the thing that makes the most sense is to fix what needs to be fixed.
Okay. Okay. I think this is from, how did you manage the TBs? And just sharing this answer from Jason by analysis and then insulating, primarily external insulation using XPS and heaps of tape.
Yeah, sorry, Daryl, I said that quite concisely. The reality is the way you deal with thermal bridges in the EnerPHit project is having somebody on site who knows what they're doing. So both the builder, Terry, and Daryl's team, when they were there on site, they would see what's going on. And as the building was deconstructed, they could see what the thermal bridge was because they know what it is and know how to deal with it. I did the math because I'm good at math. But the reality is the most important step was knowing where the thermal bridges are. And that required with somebody on site. In this case, the builder and Singh architects were on site was the most important step because they knew there was something that needed to be fixed. And then somebody could do the math in the background. It's easy.
Yeah, I think this is the last question. With an answer, Daryl's already answered this one, just want to share it. Was the original membrane to the warm roof on the Piha house acting as a drained cavity? And Daryl wrote, the original rubber membrane was left in place to serve as the air tightness layer and vapor restrictor. The double layer torch on layer over the double layer PIR boards was the weatherproofing layer. That's great. I think that's, just check.
Also, just another comment about the PR house. I think, Jason, you were saying it's probably the most thermal bridge calculations you've done on any project. That PR house was kind of one massive big thermal bridge.
Yeah.
Another question, what is the thermal bridge requirement for EnerPHit component method?
So they're all the same. So the important thing for a thermal bridge is one, FRSI. In other words, making sure you don't cause any interstitial or surface mold problems. And then two, it's energy loss. So the thermal bridge is added into the assemblies. If you look at when you pop it out in PHPP. So if you're in, I forget now, I'm sorry, I'm looking at the slides. I can look. If you're in Auckland, you have to have a certain criteria for the external air envelope to external air, and the thermal bridges that are through the walls or through the roof get added into that number. So you can compensate for the energy loss of a thermal bridge by putting more wall or roof insulation in, just like you can in a passive house. But the local moisture problems need to be dealt with completely. Like, you're not allowed to have any moldy surfaces in EnerPHit, period. Like when Priscilla was talking earlier about not retrofitting walls on the inside in order to preserve the facade, you'd have to show that that facade was not going to have any mold problems, or else to be a non-starter for EnerPHit, no matter how good you did everywhere else.
Wonderful, thank you. Thank you for that. I think that's all the questions I have, but if you do have any more questions, please email it to us at admin. And I want to thank all the main sponsor, Envelop, and all our speakers, Priscilla, Daryl, and Jason. Thank you. Our next talk, series 4, is on the 22nd of July, and it's about passive house schools and communities. So thanks everyone, and have a great day. See you all soon. Bye.